So that was the first half of today's part. The next part is implementation. So we're gonna create something called very simple file system called VSFS. This is a software file system, so we're not gonna have any hardware features. So the things we wanna learn here is that what structures are needed on the disk, what do they need to track, and how are they accessed. So two key parts in understanding file system is, first of all, is the data structure. So what types of on-disk structures are utilized by the file system to organize this data and metadata? And typically these are array of blocks, but in a more complicated, advanced file systems, they would typically use tree-based structures. Now, for our purposes, we're just going to use array of blocks. The second part that we need to consider is the access methods. In other words, how does it map the calls made by a process such as open, read, write onto the structures? What structures are read during the execution of a particular system call? What are written, and how efficient are these steps performed? So, overall organization of the file system. Let's just divide the disk into blocks, and let's say the blocks are of size 4K bytes. So, and we're going to address them from 0 to n-1 because we have n blocks. So here, from 0 to 63. Now, most systems, it will be user data that eats up most of the space. So we're going to have a fixed portion of disk for user data. And we're going to mark them as data region with capital D. Let's say we use 7/8 of our whole disk for that. Now, for the first 8, we're going to need some information about the file system. And first of all, we need inode table because we need information of all the files in the system. So we need a portion of the disk that holds the array of on-disk inodes, and we're going to use about 5 blocks for that. Now, the file system needs to track whether all these inodes and data blocks are allocated or are actually free to use. There are 2 ways to do it. One way would be to use something called a free list, where it will point to the first free block, and that block will point to the next free block, and that will point to the et cetera, et cetera, et cetera. For simplicity, instead, here we're going to just use a bitmap. So we're going to have one for data bitmap, and we'll also have one for inode, called inode bitmap. So we have 1I, 1D here. So each bit indicates the corresponding object block is free. Then we'll mark it 0 or in use. We're going to set that to 1. Now we still have 1 block remaining here, and we're going to name that super block. So this contains information about this particular file system. Basically, it means how many inodes and data blocks are in the file system, where the inode table begins, and also a magic number to identify this file system type. So in our case, VSFS. Now, when we're mounting this file system, the OS would first read the super block to initialize various parameters and then attach the volume to the file system tree. Okay, so everything starts with the super block. Now, inode, we talked about inode. But we didn't really say what I stands for. It's index node. So each node is referred to by a number called inumber, which is the low-level name of a file. So given an inumber, you can calculate where the corresponding inode is located on the disk. So with just a number, we need to be able to know where it is. So let's use an example for this. So remember we had a super block, I bitmap, DB map, and the inode table starts from here, right? Now inode table is 20 kilobytes in size. There's 5 4K blocks. We have 80 inodes, and let's assume each inode is 256 bytes, and inode region starts at 12K bytes. An example we're going to go through is, let's say we want to find inode number 32. It's pretty simple. You just want to calculate the offset into the inode region, right? So this is node number 32. So 32 times size of inode, 256 bytes. So that will be 8K, right? Then you add the start address of the inode table, which is 12K. So it's basically 20K, right? Simple. That's why you only need a number. Now, however, the disks are not byte addressable, but rather consist of a large number of addressable sectors of 512 bytes. So to fetch the block of inodes that contain node 32, the file system would issue a read to sector 20 times 1024, and you divide it by 512, which is 40, to fetch the desired inode block. So in general terms, this is the equation you would use to locate the block and sector. Yes, talked about metadata. So inode contains metadata of a file. So we could actually call metadata as any information inside the file system that isn't pure user data, right? Other than the payload, every information we need. So yeah, these are all the information there, mod, is this readable, writable, executable, user ID, who owns it, what's the size, when was last access, when it was created, etc., etc., etc. So these are the metadata that inode contains. So to access this, a direct pointer would point to a block that contains that user data. However, we could use indirect pointer that points to a block that contains more pointers, and each of which points to user data. Now, an inode may have some fixed number of direct pointers, for example, 12, and a single indirect pointer. And then if a file grows, the indirect block is allocated from the data block region, and the inode slot for an indirect pointer would point to it. Now, if you assume there's 4K blocks and a 4-byte disk addresses, then that would add about 1K more pointers, and the file can grow to be about 4K. If you want another level, you can keep going, right? Double indirect pointer, which basically refers to a block that contains pointers to indirect blocks, each of which contains pointers to data blocks. And in summary, you can actually support files that are over 4 gigs in size, and you can go through triple, whatever you want. But we're just going to use that multi-level index, and then you will have an imbalanced tree. And why would anybody do this? Well, people did some measurements, and they found out most files are very small, right? So you're going to have a large number of files, each taking up very little space. Most common size around 2K. Then in those cases, you want to optimize the system, then you might want to have multi-level index. Directory. So directory basically contains a list of entry name and inode number pairs. So each file or directory inside a directory, there's a string and a number in the data blocks of the directory. And for each string, there may be also lengths, assuming variable size lengths. So if you do ls, for instance, this is an inode number, record lengths, string lengths, and actual file name. So obviously, you have a very long file name, then the string length will be longer. Record length is actually a string length plus whatever remains. So when you read, write, create, delete, and all that stuff, there's free space and you want to manage it, right? So you need to track which inodes and data blocks are free to use. Because when you're creating a new file, you have to decide which to use. So, so the file system will have to search through the bitmap for a free inode. Then you allocate to the file. Then you have to mark the inode as used. And you also have to update on this bitmap, right? So there are many things you need to do to actually manage the free space and creating files. So to understand the importance of this, we're going to go through an access path of reading a file called -foo-bar from the disk and then writing. So if you want to open a file called bar, you need to have an information, right? Now, initially you got no info, so you have to go from the top, which is the root, right? So you're going to have to first read the root inode. Now, how do I know the root inode, right? So typically in Unix system, the root inode is 2. And it's this decided, right? Because there's no other way to get it. So you go there, you read it, then you're going to have to read the data to find out that you need to go to directory foo, right? So then you go to foo inode. You get the foo inode, then you access the data to go into bar inode. And this is just for opening, right? In order to read, you have to open a file. You have to locate the file, you open it. So there are many reads just to actually open a file. And once you open it, right, you have a bar inode, initial data read, and then you have to write. Why? Because you have to update the last access time, for instance, right? Because inode needs to have all the information, right? Then you read the next part, the next part. So here, obviously, if you have a larger directory, more reads involved. Write, on the other hand, let's say we're creating a file and writing it, okay? So here, you look at the inode, you read, then the important part is that you need to actually read and write the inode bitmap, right? Since you're creating a file. So now you're touching on the bitmap side. And then since you're creating in a directory in foo, so you need to write here, then you have to write the inode and also the foo inode, then that's the create part. If you need to write, again, you need to read the inode of that file. You need to update the data bitmap, read and write, and then you write the actual file and you update the inode of that file, etc., etc. So the takeaway message here is the read-write, which is pretty simple operation, incurs a very ginormous number of I/O operations over slow disk. So as a system engineer, our job is to optimize. And what are some ways to do it? 2 things to do. And as is in other cases, we love to use something called cache, right? So you actually want to have something that use commonly into the memory. So how do we do this? One way is to actually use a fixed size cache. And we allocate this size at the boot time, typically, let's say about 10% of the total memory. And this one is called static partitioning because we do it at the boot time predetermined, right? Now, one might argue static, simple to implement, but may not be very efficient. What if I don't need 10%, right? So to counter that, we have dynamic partitioning. Here, we actually integrate virtual memory page and the file system page into a unified page cache. So things are more dynamic, and you can do caching this way. The other way is write buffering. So instead of writing immediately, unless you f-sync, we buffer it for about 5 to 30 seconds. Obviously, there are trade-offs, right? If you buffer longer, you can be more efficient. But what if there's inconsistency and so forth? And depending on application, you might not tolerate it. But anyways, the file system can batch some of the updates into a smaller set of IOs, right? Now, since you buffer it and you can batch it, you can even schedule the subsequent IO, right? So we learned through many different scheduling, right? Depending on what you want to do, what you want to optimize, we can even schedule. Also, if you delay it, there could be cases where somebody actually create a file and then delete a file right away, right? So those kind of stuff you can avoid, right? So there are some benefits of delayed writing, and which we call buffering. Yes, that's it for today. Yes, sir. Yeah. 14. Do this. This one or 14 of, okay. 44. This one? Yeah. So record length is basically, so this is a name plus whatever remains over that space. So sometimes you allocate, right? So when you want to actually, so later on, let's say you remove it, you want to allocate, you actually want to know what space are out there in the block. So this is a name. So your name is 28, right? But the actual size is actually, you could actually assign as many as 36. So this is the length of bytes, right? Yeah.
Slide 48.
Yeah. Why do we need a read for so okay. Oh, so it's creating, yes. So it's almost like you also need to create an inode for bar.
Right.
So that's
We
that.
have to initialize like the inode structure for bar. Right?
Right.
So then why would we need to read from this like?
Well, it's like you can't just write. There's nothing in there, right? This is sort of like a create of inode. Like it's like an initialization. What you just mentioned about initialization is the read. So this is represented as read. Yeah. Oh, good question. So can dangling occur in heart? I think I think you can still have it in the heart, but let me just double check on that. Yeah, I don't think this is specific to the symbolic, but Sabine, can you take a note on that? Is the dangling only on the heart? I mean, symbolic versus heart. Did you have a follow-up thoughts on that, or was it just a simple question? Okay, yeah, yeah. Special kinds of files. Yeah. Right. So can you, so when you say a file such as sockets, yeah, yeah. So does inode have information on that, you mean? I don't think so, but let me, yeah, let me double check on that as well. Yeah. Many questions, yes. Yeah, 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 yeah. 13. This one? Yeah. Why is what? I'm sorry? Here. This is just basically error checking, right? So it's just making sure, yeah, it's larger, or so it's basically, it starts from 0, 1, 2, right? So this is just basically making sure there's no, because you never know. It's like a good habit, really. I mean, if you don't have this, is it the end of the world? Probably not. Yeah, I mean, yeah, there was more question before you there. Let me just go here. Yeah. This one? Yeah. Okay, so the question is, does the P thread share file entries? So you mean if it's duped, does it share file entries, or can you elaborate the question? Yeah, I don't think I fully understand the question. Maybe can we take it offline after we're done? Yeah, yeah, yeah. Go back to, yeah.
I think I had a side question with this. So
Yeah.
We forward. So if we make a new process, then we're going to copy the file description table. But then we're going to have to share the open.
No, no, no. So we forked it, then you can share it if you want, right? So we had an example here where you forked it, right? And you share, right?
So here we need a copy of the file description table for the child process.
Right. So it's not even a copy. You're just pointing to the same thing. Right.
And if you're working with threads, does it work the same? Do we also share the file table? We're not talking about parent process child.
So here what we mean is basically, so you have different processes, right? And they could actually share if they want to, right? Because there are some cases that's useful, right? Now, depending on the threads, right? So if the threads, if a different threads in a process, if it's good to share, then you can go share, right? So are you saying, is it by default? I mean, because it depends on which file, right? And if you need to actually share it, then you use the same file descriptor. Right, so, I mean, this is basically example of, because this is a per process thing, right?
Yeah, I was thinking of like a case where like, where parent process and child process,
Yeah.
they're working on a file together.
Mm-hmm.
It's the same file.
Mhm.
The child closes that file. The parent will still have that file open. Then if you're working with threads, if the one thread closes that same file, will the other thread, the main thread, have that file closed?
Okay, so I see your point. Because you're saying instead of process, you're going to the thread level, because we had like a reference count, but does that apply to thread? Okay. Yeah, I'll have to look that up. Yeah, yeah. Was there any other question? All right, so a lot of questions. So we'll get this info up on the campus wire. Otherwise, I'll see you guys on Monday, next Monday.